In the previous slide, we have covered the first 8 quantities and derivation of their base units. Quantity number kinetic 9 is kinetic energy, and interesting thing is it's also an energy. All the forms of energies are scalars. Its unit will be joule, and its base unit will be same as work, kilogram, meter square, second minus 2. We can prove the same base unit using the formula for kinetic energy, which is 1 over 2 into m into v square. So the unit could be written as 1 over 2 has no unit. Unit of mass is kilogram, and unit of speed is meter second minus 2. Meter second minus 1 and whole square. So it would become kilogram meter square second minus 2. This is quantity number 9. There is kinetic energy. Now from quantity number 13 to quantity number, 12 to 15, all the quantities are about deformation. So deforming a wire or some object, compressing an object or stretching an object. Quantity number, okay, no, right now we are on number 10. Number 10 is power. Power is a scalar. Its unit is watt, represented by W. And its base unit, for base unit we'll go with derivation. So for power, the formula is power is equal to work over time. You know, work is force into distance divided by time. That would become MA times D divided by T. So the unit and base unit of power will become kilogram meter second minus 2, meter second minus 2 for acceleration. For distance, it is meter, and for time, it is second. Finally, it would become kilogram meter power 1 plus 1, second power minus 2, second power minus 1. So finally, it is kilogram meter square second power minus 3. It is kilogram meter square second power minus 3. So this is for power. So power is a scalar, its unit is watt, and its base unit will be kilogram meter square second minus 3. So power is a scalar, its unit is watt, and its base unit is kilogram meter square second minus 3. Sorry, it's second minus 3. It's energy over time. So this is for power. Number 11 is, quantity number 11 is moment or torque. It is a rotating effect of force. Moment or torque. It is the rotating effect, or I will say rotating acceleration basically. Rotating acceleration or rotating deceleration. So for rotational objects, acceleration or deceleration is called moment. For example, if an object is rotating with a constant speed, then its moment or torque is 0. The force that increases the rotational speed or decreases the rotational speed causes the moment, and the amount of moment can be measured as, it is basically rotating effect of a force. It is product of is product of force and perpendicular distance of line of action of the force from the pivot. So its formula could be written as, for example, if we have a rotating wheel and we want to increase its speed, then we need a force that can increase the speed of this wheel. We apply a push on the wheel in the direction of motion. For example, you're applying a push at tangent to the motion, then this push will increase the speed of the wheel. The rotating point of the wheel is at the center. So if we multiply this perpendicular distance with the force, we'll get the moment. So moment could be written as perpendicular distance. It's actually a vector and force. So if we multiply perpendicular distance of a force from the pivot and the line of action of the force, if we multiply them, then it is the moment. The unit and base unit of moment would be, unit of force will be Newton meter. As you see, force is in newtons and distance is in meters. However, this Newton meter cannot be written in terms of energy ka unit, that is joule, because joule is the capability to perform work. Basically, the rotation and the work or energy cannot be added. So by principle, the rotation and the energy are two different quantities. However, you can ask that why their base units could be same, or why their formulae are same. Their formulae are not same exactly. Work is actually product of force and displacement along the force. So when you calculate work, you multiply force and distance, force and displacement, which are parallel. So when you multiply force and displacement, which are parallel, it is the work. However, when you calculate moment, the force and the displacement, they are perpendicular to each other. Displacement is the distance of line of action of force from the force, and it's a vector quantity. So the moment, which is product of two vectors, is a vector. The moment, which is product of two vectors, is also a vector. So moment or torque is a vector quantity. Its unit is Newton meter, which cannot be written as joules because by definition it's not energy, it is the rotating effect. And base unit of moment will be base unit of moment or torque would be base unit of moment or torque would be, we can write its formula as moment is equal to d cross f. So it is d cross ma, and if we substitute the units, it would become d could be written in meters and m is in kilograms and a is in meter per second square. So finally it would become kilogram meter square second minus 2. This is base unit of moment. So moment, which is a vector, Moment is a vector. Its unit is Newton meter, and its base unit is same as the base unit of energy, kilogram meter square second minus 2. So this is the unit of moment, and the base unit of moment is kilogram meter square and second minus 2. We need to write here that moment, which is also called torque. In our syllabus, we are not going to differentiate these two quantities much. So the rotating effect of force, that is moment or torque, have same base unit as work or energy. Moment or torque have same base unit as work or energy. However, the unit Newton meter cannot be written as joules because the rotation and energy, moment represents rotation and joule represents work, represents energy. So the rotation and energy are two different quantities by nature. So Newton meter and joule, if Newton meter is representing the rotating effect of a force, that is moment, then they are totally different. You cannot even add or subtract them. So they are totally different quantities. So this is all about moment or torque. Quantity number 12 is stress. When we extend something, then the pressure is replaced by another quantity, that is stress. Formula for stress is, I will not discuss this quantity a lot right here. However, when we'll study the chapter deformation, it will be studied in detail. So generally, force over area is pressure. However, when we extend or compress something, then the force acting on a unit area, distribution of force according to area, is called stress. So from here you can see that the unit of stress will be Newton per meter square. That is also called Pascal. And if we go with base unit, the unit of stress is Newton per meter square, or you can call it Pascal. It's Newton per meter square or Pascal. Base unit of stress is, if you want base unit of stress, then it is, according to formula, stress is force over area. Force is MA over area, so it will become kilogram meter second minus 2 over meter square. Finally, it will become kilogram meter minus 1 second minus 2. So this is the unit and base unit of quantity stress. So stress, this is the unit, and this is the base unit. Same base unit as pressure. Stress has same base unit as pressure. Yet the detail of stress will be studied in the chapter deformation. Right now, we only have written the formula and unit and base unit. Quantity number 13 is strain. You are studying this quantity for the first time. However, you need to know the concept of this quantity. First of all, you need to understand if you want to check which of the two wires, which of the two given wires or ropes or threads or pieces of rubber is more stiffer. Generally, we think that the one that extends less is more stiffer. However, if we want to compare the samples, then the length will be a control factor. If you take different pieces of different lengths, then obviously their length will start to affect their extension, and as a result, the results that you achieved will not be accurate. For example, let's take an example of two samples of wire. This is sample one. A second sample of wire, that is sample two, it is here. So we have sample one and we have sample two. On sample one, we are applying a force of, for example, 1000 Newton from both the sides. On sample two, we are also applying a force of 1000 Newton from both the sides. Now let's take the length of sample one as, the length of sample one is, for example, this was, length was 1 meter and length of this sample was, for example, 5 meter. Now you extend them with equal force. However, you know that a shorter piece is difficult to extend, and as a result, the extension here that you will get, here you will get an extension of 1 millimeter. For example, the values are just for understanding. Here you get an example of an example extension of, for example, the extension is just for the understanding of concept. It is 3 millimeter. Apparently, it seems sample 2 is extending more. However, the problem here is that it's not a fair test. For a fair test, the lengths must be equal. And if you do the experiment even with different lengths, then dividing the extension with length, you can get a direct or a fair comparison. And the quantity extension over length is called the strain. So the strain is defined to eliminate the effect of length on the extension. So if we define extension over length in both the cases, here extension over length will become, extension is 3 millimeter and length is 5 meter. So the constant that we are calculating will become 0.6 millimeter per 1 meter. However, originally when we are calculating that, we will convert the units into meter. Yet right now, to understand the concept, we can go with millimeter. In the second case, if we calculate this same quantity stress, what we get without converting the units, it is 1 millimeter over 1 meter. Now you see sample 1 extends by 1 millimeter over 1 meter. And sample 2 will extend by 0.6 millimeter over 1 meter. Now you should observe which of the two samples extends more. One of them is 1 millimeter for every 1 meter. Second one is 0.6 millimeter for every 1 meter. It shows that the second sample extends less and the first sample extends more. So, however, if you only observe the extension, then it could deceive you, because sample 1 was extended as 1 millimeter and 2 was extended by 3 millimeter. The problem was that when we applied equal force on different pieces of lengths, then obviously the length of the sample or the length of the wire will also affect the extension. By dividing the length over extension, the effect of length can be eliminated and the new quantity that you get is called strain. So for strain, it is the ratio of same quantities. Strain is actually extension over not the extended length but the original length. It is a extension over original length. Unit of extension is meter and unit of length is also meter. So it has no unit. So strain has no unit or base unit. So the quantities which have no units or base units, they are called dimensionless. Strain is dimensionless. What is meant by dimensionless? Dimensionless means we'll say that a quantity that has no unit a quantity that has no unit is called dimensionless. So if a quantity has no unit, then it is called dimension. A quantity with no unit is called a dimensionless quantity. A quantity with no unit is called a dimensionless quantity. That's why strain is a dimensionless quantity. So for strain, we will write that strain has no unit and also it has no base unit. Strain has no unit and also it has no base unit. So strain has no unit and no base unit. So this was about strain. Number 14 and 15 are the quantities that we have to study in detail. So they're very important and very conceptual. They are the conceptual quantities. Number 14 is Hooke's constant. At your level of physics, sometimes instead of focusing on the concept, we focus on the understanding. So right now, I will try to explain the Hooke's constant and Young modulus in a very understandable way. That what they are, what they represent, and all of that. They both represent same thing, stiffness. And here I will say stiffness is difficulty in extending something. Hooke's constant represents stiffness of a sample of wire, for example. You may say a wire is a cylindrical shape. And Young modulus, instead of a wire or object, it represents the stiffness of a material. So basically, if you want to see the stiffness of a wire, if you want to compare the stiffness of different wires, then the quantity that you're going to use is the Hooke's constant. So Hooke's constant is used to compare the stiffness of individual wires. However, if you want to compare the stiffness of the material of the wire, then the right quantity is Young modulus and not the Hooke's constant. And one thing that we need to clear is that stiffness, as we referring it here, is basically the difficulty the difficulty in extending something. Stiffness, as we are referring it here, it is the difficulty in extending something. Now, let's define Hooke's constant. What is the exam definition of Hooke's constant? Hooke's constant basically is how much force you need to extend an object by 1 meter. If the force needed is more, then obviously the object is stiffer and the Hooke's constant is a higher value. So Hooke's constant by exam definition is force needed per unit extension. Here per unit extension means an extension of 1 meter. So Hooke's constant can be written as force over extension. How much force you need to extend something by 1 meter. For example, if a wire has a Hooke's constant of 100, it means that 100 Newton of force is needed to extend the wire by 1 meter. And if Hooke's constant of an object is 1 million, it means that 1 million Newton of force is needed to extend this object by 1 meter. So Hooke's constant, represented by symbol K, is given as F over X. Now let's write unit of Hooke's constant. Unit of Hooke's constant is, you see, K is Hooke's constant and it is given as F over X. So its unit is Newton per meter. Now the base unit of Hooke's constant. The base unit of Hooke's constant. The base unit of Hooke's constant will be K is equal to F over X. F is MA over X. So it would become kilogram meter second minus 2 over meter. So this meter will be cancelled with meter. And finally what you get is it would be kilogram second minus 2. It is the base unit of Hooke's constant. Now for Hooke's constant we can write Hooke's constant, its unit is Newton per meter and its base unit is kilogram second minus 2. So here we go with the unit and here we go with the base unit. If we want to understand young modulus, first we need to understand the concept of Hooke's constant well. Hooke's constant is basically stiffness, but it is the stiffness of the object. So first of all, we need to understand that Hooke's constant depends on 3 factors in total. Depends on the material, it depends on the length, it depends on the area. In more accurate words, it depends on the material and dimensions. Hooke's constant depends on the material and it also depends on the dimensions. This is the Hooke's constant. The difference between Hooke's constant and Young modulus is that Young modulus describes the same thing. The only difference is Young modulus only depends on the material and it is independent of shape, size, length or area. So Young modulus is also a constant of stiffness that measures the stiffness, yet it is independent of length, area or other dimensions. Basically, the two quantities Hooke's constant and Young modulus serve different purposes. Let me give examples for that. Compare stiffness of 10 wires of copper having different length and area. So if stiffness of 10 copper wires with different length and area is to be compared, then you have to use, since all the wires are made of copper, so length and area are the independent variables, so you have to use the Hooke's constant. The values of Hooke's constant of copper wires can give the comparison of their stiffness. However, if the examiner asks you to compare, the stiffness of steel and copper as, however, if the examiner asks you to compare the stiffness of steel and copper as two different materials, then in this case, the length and area is irrelevant. You have to use Young modulus. Use Young modulus. Use Young modulus for this comparison. So if you want to compare the stiffness of different wires made of same material, or you want to see the effect of length and area, use Hooke's constant. Yet if you want to see purely the effect of the material only, then you have to use the Young modulus. The Young modulus is independent of length and area and shape and size. It only and only depends on the material. Now, formula for Young modulus. We can use the formula for Hooke's constant to make a formula for Young modulus. For example, Hooke's constant K can be written as F over X. Now K depends on area and length. Why it depends on area and length? Because force needed to extend an object by 1 meter, this F is force needed. This x is how much extension you will achieve. Actually, F is force needed for 1 meter and x should be an extension of 1 meter. Yet, how much force is needed to extend an object by 1 meter? It depends on the area of the object. Thicker objects extend more. Thicker objects extend more. However, if you see, the longer wires extend more. The extension depends on the length. So these are the two things which explain the dependence of K on area and dependence of K on 1 over L. Since X is in denominator, if you double the length, extension becomes double. If you triple the length, extension becomes triple. Same is for force and area. That's why we get this type of relationships. And from these relations, we can see another interesting thing. For example, if this is area and this is force, and I ask you to calculate force over area, then for an area of, for example, A, the force is just, for example, F. For a certain area A, force F is needed to make a certain extension. For the same extension, if the area is doubled, the force will become double. If the area is tripled, the force will also become triple. If the area is made 4 times, the force will also become 4 times. This is we are doing within limits of proportionality. Yet, for basic understanding, this is the relation. Now, if you divide F over A, this would become F over A, this would become 2F over 2A, this would become 3F over 3A, this would become 4F over 4A. So I believe every time, even if the area is changing, the F over A remains constant. Because if the area becomes double, then the force needed for the same extension also becomes double. And this quantity F over A, which is called stress, is not depending on the area. So the answer is F over A. The answer is F over A. The answer is F over A. The answer is F over A all the time. The answer is F over A all the time. Even if you are changing the area, F over A remains constant. So we can make a conclusion. Although F depends on area, yet F over A is a constant as it is independent of the area. So you can say that F over A is independent of area because if you double the area, the force needed will become double. And as a result, this F over A will become independent of the area. It does not depend on the area. Same is for extension. If we go with the original length and the extension within the limit of proportionality for a certain force, we can say that, for example, length was L and extension was X. Length was 2L, extension becomes 2X. Length was 3X, extension becomes 3L. Length was 4L, extension will become 4X. And if you divide extension over length, every time it is X over L. So this is constant. This is independent of the length. So extension depends on length, yet X over L is independent of the length because if the length is double, extension will also become double and so on. For example, X over L will become, if it is 2L, it would become 2X. If it becomes 3L, it becomes 3X. As a result, it is X over L. It is X over L. So it is extension over length all the time. So strain, this quantity is called strain, as you know. So we can modify the formula for Hooke's constant in terms of Young modulus. In this formula, F depends on area, extension depends on length. Now, what if you divide force by area? Dependence with area will be eliminated. So this K will become Young modulus if F is divided by A. Now, when you divide force by area, since they have a direct proportion, if you double the area, the force needed becomes double. And as a result, the F over A term will remain constant. In the same manner, if you divide X by L, if you divide X by L, then the dependence with length will be eliminated. So the Young modulus will become, so basically the Hooke's constant formula has been modified into Young's modulus formula by eliminating certain factors. Young modulus only depends on the material, while Hooke's constant depends on the material length and area. So length and area have been eliminated. So the quantity in the denominator is called stress. The quantity in the numerator is called strain. So Young modulus can be written as stress over strain. As you see, strain has no unit. Now we have two things. Hooke's constant, it is a measure of stiffness, but it measures the stiffness of different objects and it is affected by the length and the area. The other constant is Young modulus, which also measures the stiffness or difficulty in extending. However, it is not depending on the length and area, and it is only depending on the material. So you can say that Young modulus will have same unit and Young modulus will have same unit and base unit as stress, because strain is dimensionless. So we must say that Young modulus will have same units as stress. Its unit will be Newton or meter square or Pascal. And its base unit is kilogram, meter minus 1, and second minus 2, same as pressure. So its unit and base unit is same as pressure. So this was about Hooke's constant and Young modulus. I believe you would have understood this. Hooke's constant and Young modulus, both of them tell the stiffness of a material. Stiffness. Stiffness is basically difficulty in extending. However, Hooke's constant is used to compare the stiffness of different objects, and Young modulus is used to compare the stiffness of different materials. We have to complete till here in this class. From here on, we'll continue in the next class. Inshallah, the next slide will be from quantity number 16 to quantity number 24. Take care, students. Khuda Hafiz.